So I'd like now to introduce Christoph Reinhart. Christoph is a building scientist and architectural educator working in the fields of sustainable building design and environmental modeling. At MIT, he leads the Sustainable Design Lab, which is an interdisciplinary group with a grounding in architecture that develops design workflows, planning tools and metrics to evaluate the environmental performance of buildings and neighborhoods. Design tools originating from the lab include things like Diva, UMI, MapDwell and DaySim, and they're used in practice in over 90 countries. So would you join me in welcoming Christoph?
Thanks a lot, Paul, for having me here. Thank you all for coming. I actually just figured out that I forgot to wire myself. So bear with me a second. Is this on? So we got this all planned out. Yeah, it's on. I think we're all good. So welcome. Thanks a lot for joining us this evening. I'm keen on sharing some of the results from our lab. Before I actually start with a presentation, it would be wonderful to get a sense who here, Paul warned me or promised me there would be architects in the room. So who is in the architectural domain here? One, two, a few of you. Oh, fantastic, great. Now that's because I built in some of our work that's more related to work at the individual building and the architectural level, and architectural education is very important to me. As Paul already mentioned, our lab is called the Sustainable Design Lab. Most of us have a background in architecture, but they also then usually know a lot about building technology, obviously, and about computer science. And the overarching goal of our work is to change current design practice. And what we mean with that is that we are observing how architects and urban planners work, both in the studio as well as in practice, if we get access to that information. And then we try to design workflows, metrics, tools that improve current modes of practice and then hopefully lead to better buildings. And the bread and butter behind what we are using is this field called building performance simulation, which is the computer-based attempt to model the various heat and mass flows in and around buildings. And that sounds pretty dry on the one hand, but on the other hand, this allows us really to model the whole human experience, wherever we are, within building, outside of buildings. How warm are we? How much light do we have in our face? Are we comfortable? Are we productive? And so the applications of this basic physical phenomena allow us to answer a whole variety of questions. Now, why would somebody use this? This is some really basic introduction here. Why do you want to model the built environment before you actually build it or in parallel to it? And there are two main applications for that. One is to demonstrate doing design code compliance. So if you think of the LEED rating system or something like this, that we are showing that this building is doing better than other buildings. For us, this is the more boring application. We really want to do the old tested and true checking if a certain design, if you have a design idea, we want to analyze the design and then to redesign the building and make it better. And that is a very old basic idea, and it's surprising how often it doesn't work. What you are seeing here is a survey that we did a couple of years ago where we asked about 100 mostly US design firms that all use simulation in their practice. How often do the simulations change your design at all? And in the left column, you see firms that have in-house modelers, so that are big enough or that work very closely with consultants so that during the design process there's an exchange. And there, in my slides, yellow and orange is usually good, so we have a lot of yellow and orange. So there was a sense that there was a lot of buy-in, whereas when you use the firms that at the end of the design process have the LEED simulation done, then the effect is very small. And our goal overall is to get the whole bars orange over time. We did something very similar with a very large American AEC firm, did a representative survey throughout their firm and wanted to know both from the designers as well as from their simulation expert, same question, how often do simulations influence your design? And it seems to be getting worse. It might be that people have more ambitions nowadays, or it might just be that the way we are communicating results are not effective enough. So is there any hope? We also asked the same group, well, is there a willingness for change? Do you at least want to learn how to use the tools? And then really nicely, if you look at the bright yellow again, that there was a very large number of the designers within the firms that want to learn how to use performance simulations to change the design process. So I think there's a key moment right now that we have to seize and hopefully convert as many becoming architects into also individuals that know how to model their buildings in situ while they design their building. And that leads to, in a way, to the question, how should an effective design tool look like? And this is a couple of years old. This is a collaboration that we did with the MIT Media Lab, where we designed a Lego table-based simulation environment. So what you see here, this is the planning board in Riyadh in Saudi Arabia, and this is a square kilometer in Riyadh. And there are 18 different Lego pieces that they could distribute, and we have then a real-time simulation that scans from below the building typologies and then provides information on energy, walkability, and daylight, access to light onto that Lego model. And the advantage was really that we had a very engaging tool where we had, after half an hour, the planning board argue in Arabic whether you could build something that way or not. So that was very positive. On the limitation, I think these type of interfaces are limited when it comes to how detailed you can really go within the analysis. So there's always this trade-off, how you make it accessible to people and provide the right amount of information. So for today's talk, I tried to break up our work first into some very basic summary of what do we know about computer models today, how accurate are they. Then I want to talk more at the building level, what kind of metrics we should be using and how can we teach these tools in practice. And then finally, I talk about our work that's more related to the urban level. So simple question, if you are just starting out or you already know about these tools, what should you say when somebody asks you, do these tools work? And there on the energy side, we have done a lot of work for over 40 years. We go back into work, a lot of it done in the UK, where we had these little test boxes and we were measuring temperatures and modeling them. So at the core, these engines managed to model what at the time was called solar architecture, so temperature distributions that change over time. That we can do, which is good. And the field has, at least in the US, become quite established. You can now become an energy modeler according to ASHRAE, and you can have a software that's ASHRAE certified. So that all exists. The key driver within the US was really that the IRS, the Internal Revenue Service, became interested and developed trust in these tools as well. So nowadays, when you model a tool during the design process and you can show any savings and you quantify the savings, you can write them off your taxes in the coming years. And that was, of course, a good way of paying for the whole community of people that do this type of analysis. So if we now go to, actually, I'm always interested in what design teams are creating during the design process and how reliable that is. So what you see here is a comparison between simulated and measured energy use. So this is simulated during the design phase, and this is the measured energy use during the first year of operation. And if we had perfect use of tools and perfect tools, you wouldn't see any of these dots. All these are the first generation of LEED certified buildings. Everything would be on the identity line here. But of course, what you find, some buildings are doing better than predicted and all the large buildings are doing worse. And that's typically showing to an issue that we have with large non-domestic buildings, that we have a hard time predicting how they're being used and how to operate them properly. But when you look at this, you could say, well, maybe the tools just don't work. And just to give you some sense that this is not the case, we worked with a company called NR Modal on a whole series of buildings, used their first year design phase models, calibrated them with very limited effort because we want everybody to do that. And you see here from before to after, you see these orange triangles moving more and more to the identity line. And there's been a lot of work by the National Renewable Energy Laboratory also showing that the simulation tools for energy work. That's just something to keep in mind, that at least when you do everything right, you should be able to predict energy use in a building. How does this work for lighting? And lighting is, of course, something that's a key architectural concern. And I think there's always the confusion what a lighting simulation is, right? So what you see on this picture here, this is the extension of the Harvard Art Museum's by Renzo Piano, this lantern, very nicely impressive daylit space. And here you see different ways when we ask the design team, so what is your lighting simulation? And even the sketch of the building can be considered to be a type of lighting simulation, getting a sense of how the building is actually going to perform, even if it might not be reality, but it expresses the designer's desire, how the space should look like. And then, of course, typically we have these architectural renderings that are meant to, again, communicate how a space is supposed to feel. And then at the top, at the lower right-hand corner, we have the actual physically based simulation. So this is really a measurement used in Radiance, where every pixel in the image gives you an absolute luminance levels. And that's what we want to create. And I think it's very important that we are all aware that there are these different ways of how to communicate light within buildings. Within in our world, we are mostly concentrating really on this measurement slash simulations here. And what do we know there, how well they work? Well, about 20 years ago, we did all kinds of measurements and simulations in spaces where we went into full-scale spaces, used illuminance meters and measurements, and we got very good results. So what you can remember is that we can model daylit levels in buildings with a relative error of about 20%. Which is really, really good because your eyes are logarithmic sensors as well, and your eyes are not better than the simulation. So we can basically model on par with how well we can perceive a space. And now more recent work looks into not only looking at illuminance meter readings in spaces, because that doesn't say anything about the quality about the space. So we are now moving towards high dynamic range full images of a space. So what you see here is on the left-hand side, there's a photograph of a space. Every pixel corresponds to a luminance measurements, and in the center and on the right-hand side you see simulations, and you hardly see a difference. So we basically can show that these type of simulations can model really the full human experience, how we experience brightness in a space, and that helps us then to look at visual comfort in reliable ways. And finally, one key concern is always speed. So this is a new engine based on Radiance that Nathaniel Jones from our lab developed, which allows you to effectively walk through a complicated space. This is the GSD at Harvard. And you get in real-time feedback on how bright it's going to be and how much glare you're going to experience within the space. So we have a lot of hope that these type of engines will be used here in a virtual reality setting, that you live walk through your building and you can capture the moments within the space when there's too much light, where there's discomfort, and so forth. That's one development, that we try to make our engines fast. Another large key topic has been what we are actually modeling. So for the longest times, we've been relying on this one curve. This curve is our daytime vision and shows us how the photometric curve, how sensitive our eye is to different wavelengths. And that then is converted into a signal how bright we are experiencing a spot. But now, and this is our daytime vision. If you don't remember from your basic building technology curve, this is your nighttime vision. But now we know there's also a third type of cell within the human eye, which is more related to our light and health, how awake we are within the space. And what's, of course, is very interesting that our ganglion cells here have a different action spectrum than our daytime vision. And that leads now to this interesting moment where we can start to separate designing lighting for visual information as opposed to lighting for how alert we are within the space. If you want to do that, you have to go beyond modeling a space just in red, green, and blue, but model the full spectrum, effectively. So this is something that we've been working on and we just released. Here you see a situation, for example. Here you see two students from our lab. One Alpha is drinking espresso every morning to keep awake, and Jamie is using this blue light source to keep him awake, and he's drinking some terrible herbal tea, but ultimately we can say we get the same effect. You can also combine the two if you want to really be awake. So this is what we want to do, to kind of start introducing this basic science that we know now about alertness and do spectral modeling. And in order to do so, we have a new tool out that's called Alpha for adaptive lighting for alertness. Here you see an internet cafe on this picture. In the corner here, there's a bookcase. It's supposed to be more cozy and very blue, red enriched light, whereas the back space here and the side is daylit, so we want a more exciting space. So what this Alpha tool effectively does, it breaks up your whole floor plan into these different quadrants, and it tells you when you're here indeed, when something is very blue, it means we have blue enriched light, so you will feel excited within the space, no matter which way you're looking. Whereas in the corner here, when you are more in the back, you have a more calming effect. So this effectively allows us now, in a very short period of time, to design our spaces and not only say, can people actually see or do they experience glare, but also look at these other aspects of visual comfort within a space. And then when you're using the tool, you can effectively place yourself at different levels and survey the whole space in a very short period of time. So with this section, I really wanted to talk more about what are the different components, what can we model today. And effectively, we can model energy and the visual environment around us with a high spectral resolution. So that gives us a lot of data in principle. Now, of course, the question is what we're going to do actually with that data and how do we teach people to use that. And there, I'm going to cover that only very shortly, but what we've been doing for a long time when we talk about the quality of a space, we say we have basically 3 different criteria for a high-performance building that we want to take into account if we want it daylit. We want the daylight availability, so we want to make sure that there's light in the space. Then we want to understand visual comfort, how people are going to react to that light. Is it too much, not enough light? And what effects does this have on energy? And of course, the most interesting part is this kit in between, which is the occupant behavior and the controls. And there are a whole variety of different things. I think the most interesting part are spaces like this. This is a nightmare for any energy modeler because the occupants can do everything, right? That she can open the windows, lower the blinds, turn on the lights, and it becomes very hard to predict what actually happens within the spaces. There's a whole International Energy Agency task that tries to understand better what people will do here, and then there are some stochastic models that cover this. And then there are other spaces. This is very easy to model. This is the Rolex Center by Sana in Switzerland, where the occupants can't do anything. Everything is controlled by clockworks and the sun, and basically all these blinds close and open at the will of Rolex and I guess the building designer. And then there are these very deliberately designed spaces, such as the New York Public Library, where there are no controls, but when you go in that spaces, they were designed with their shape and form that direct sunlight never hits the working areas, so they just work by themselves. And finally, another way that's probably, again, my favorite, that's the Rolex Center again. There are 2 ways of how to look at visual comfort in buildings. One is to say we have predetermined workspaces, and we have to make sure that nobody experiences glare when they sit at these workspaces. Or you just give up all the furniture and give everybody beanbags in the building, and then they just move around and pick where they want to sit. And that's kind of taking adaptive comfort to the limit, right? Nobody's going to experience glare in this building because they just move around. And I think when we design modern spaces now, we have to try to take all these somewhat into account. So quickly, how are we looking at these 3 different metrics for daylight availability? We are using, and increasingly so all over North America, this metric called spatial daylight autonomy that models for a whole year how much light there is within the space. And then basically, the daylight autonomy tells you what's the percentage of the time over the whole year when you're in the space and you get more than 300 lux. And if it's more than half the time that you're in the space, then we call the space daylit. And that effectively allows you to divide any building anywhere on Earth in a daylit and a non-daylit portion. Now, in In the UK, I think there's something that's called useful daylit illuminance that's used instead, where you have an upper and a lower limit. I don't want to get into that too long. I just generally think that is not necessarily true. So this is a picture taking. This is not staged. There are 10,000 lux. Andy works on this space and still can see fine. From where the picture was taken, you only see the sky, but with modern screens, you can actually work with your laptop in 10,000 lux and you have no problem. So it's not the oversupply of light, it's basically visual or thermal comfort that might change it. So I'm a fan of saying we are using daylight autonomy to say, do we have enough light? And when it comes to an oversupply, that becomes a question of visual and thermal comfort. So what is an oversupply? And we are using for oversupply glare, something that's called daylight glare probability, which is a metric, an algorithm that you can apply over a high dynamic range fisheye image that gives you a percentage of likelihood of glare for somebody, that somebody experiences glare within a space. So here on the left-hand side, you see, for example, somebody working at a desk with horizontal Venetian blinds open. The problem here in terms of visual comfort is that the contrast within the field of view is too high, so you have disturbing glare according to the metric. And in the right-hand side, we are sitting right within the sun. It's just way too bright to do any work on the screen in this when you're facing this way, and so we say it's intolerable glare. So we favor basically the combination. We use daylight autonomy on the one hand side to say if there's enough, and then we use daylight glare probability over the whole year to see how often are people experiencing glare. And then the tricky part about visual comfort is, of course, it matters so much which way you look, right? Because I can look one way towards the sun and then I experience terrible glare. But then I shouldn't look that way. I should just look the other way. So we are trying to give people this freedom to evaluate a space and say how easy is it for them to move within the space and adapt. And then if you look at this type of analysis over a whole year here from the 1st of January to the end of December, if this poor guy has to sit straight at the screen all year and can't move, he or she is going to experience glare all the time. But if we just supply a small window of opportunity to adjust their work position, you can take care of glare to a pretty large amount in this case. And then all of this is basically feeding into how much energy one uses within the space. So from our end, we would then use daylight, visual comfort, and glare to evaluate all kinds of different facades. So as an example here, you see a south-facing facade with blinds, with split blinds, with an overhang, with a translucent system, and with switchable glazings. This, what I just described to you, provides a framework that allows us to look very quickly of a whole range of different facades and say how people feel under all these kind of analysis. I'm running out of time to get to the energy modeling part, urban modeling part as well. Just in terms of how are we doing this type of analysis, we're using a software that is called Diva for Rhino, which is a Rhino-based plugin that allows you to do this type of analysis. And I also wanted to talk about, since we're at the School of Architecture, how you teach that actually, and that's really important for me. We teach this type of analysis in first semester at MIT to the architecture students, all architecture students, and we basically want them to teach building science by use simulation to explore if what they learn, how this would apply to their actual building. And there's a lot of information on our website, but I just want to give you a snapshot. Basically, we start, this is first week. We have everybody create a 3D object, put it in the sun, and take a picture twice a day. And there you see the shadow. And then they have to model this. And that creates instantly this trust that there is this correspondence between the digital and the real world. And then as we go through the weeks, after a couple of weeks, they take photographs of spaces and measurements, and this is the simulation, and they should be as close as possible. So with lighting, we try within 4 or 5 weeks to give them the tool set to model spaces that they see. Lighting is a lot easier because people can see light. It's very easy to go into a space and say, yeah, it works or it doesn't. Energy is harder for us to basically teach. What we are doing there is we started this simulation game, which is instead of a midterm, the students have to form groups of 2, and in 90 minutes they have to design the most energy efficient building that they can within a certain budget. We give them $50 MIT, and the budget basically tells you what kind of upgrades can you do. And when we first did the game, basically, we didn't let the students do the simulations. We had the experts, and then people could go like in a supermarket with their simulation order form and say, I want better insulation, and I pay for better lighting systems. And based on that, they got a simulation result. Nowadays, we do the same thing in Grasshopper and Rhino, and we now have a whole series of universities that play that game as well. So the way this works, you just sketch out, you mass out your building, you say what kind of upgrade you want to do, and you get your results back in real time. And for example, very hard when you're a designer, when you make your windows smaller, you get money back. And everything else, the price goes up, of course. And that tends to work very well. You can effectively go through 40 different ideas for your building in 90 minutes. So this was just, and if you want to learn more about all of this, we do once a year something that's called Diva Day. And that's a symposium where we talk basically about how we are teaching these tools, and then we try to understand from different design firms how they're using the tools. The last one was at UC Berkeley. The next one will be this fall at Cornell, the Cornell space in New York City. So I'm covering a lot of ground here, but now I really want to move towards how can you use the same methods that we've used for the last 20 years at the individual building and apply them to a whole city. And for that, one should, of course, always ask you, who is interested in that? Why should we model multiple buildings at the same time? And then, of course, the world's going to town. We have more and more people living in cities. If you put that in numbers, the numbers vary, but we got a net influx of about 2 million new city dwellers worldwide every week. And if you just think if all of them would move to London, how many buildings would we have to build? I don't know how dense you're living here. If they would all move to Boston, we would have to build 400,000 new buildings every week. And if you compare that to the number of LEED certified buildings in the world, there are about 90,000 buildings right now. That shows you right away that if we don't start expanding our efforts from the individual building to the urban planning issues, we are not going to be able to catch up. But then there's another trouble. We cannot just look at energy use, because if we look how people in the world live, from the informal settlement to the lone plus energy home, then when you just look at energy, probably the informal settlement is doing better than a lot of planned neighborhoods, but the plus energy home would be doing better. So we could fall into the trap of telling everybody to live in a plus energy home, which doesn't reflect the reality, of course, of the living conditions. So we have to develop a modeling environment, we felt, that looks at multiple levels of urban performance. And so if you want to try this, we have our tool is called the Urban Modeling Interface. It's a Rhino plugin that has a whole range of different performance criteria, from energy to mobility, comfort, access to light, finance, and now even food production within cities. And you can download it from our website, and I give you some examples on its use in the following. So the first time we wanted to use the methods that we've used at the individual building level to a whole city level was a couple of years ago, 3-4 years ago. And there we looked at solar maps of cities. So the way we created a solar map of Cambridge was, this is a snapshot of Cambridge where MIT is located. We used LiDAR data. We converted LiDAR data into a 3-dimensional building model. We calculated for every rooftop in Cambridge, for every hour in the year, the temperature and the solar radiation falling on that rooftop. And we converted that, here you see it, into this solar map called MapDwell, which exists now for 8 different cities. So the way it works, you effectively, you type in your address, you get your roof, you draw where on your roof you would like a PV system, and then you get instant feedback how much you would pay for that system, how much you would get back, how many state incentives you get, and payback times and yield. So our goal was from the get-go to have people do this back-of-the-envelope analysis where we say, okay, in 5 minutes I know how much would I pay to get the system in place, what's my payback time, and how important is that to my overall energy use. And that field study is something that we did in 2014. We worked with a company or a local NGO called Mass Autobahn on Cape Cod. We did a Solarize program where they went from house to house and said, look at this PV map, try it out. We had, I think, 80% of the town tried the map, contacted the installers, and then basically you see this breakdown here where when the installers were called, in 44% of the cases, they just looked at the map and said, oh, your roof isn't good. We are not even coming because the roof might be shaded or the orientation might be bad, whatever it was, they didn't come. When they came, in 94% of the times, they made an offer to the owner, and in 54% the owner basically said yes, which is an amazing statistics if you're in the solar market, because usually you don't make offers all the time. I think you do an offer 30% of the time, and then of course in most cases the owners change their mind. But in this case, this shows you the advantage of having a platform where the person offering a product and the person wanting to buy the product uses the same type of information, which of course has to be correct, but then you get buyer and seller way quicker together. So in this case, we had, in 4 months, 10% of all the households bought a PV system. And we want to, in the long term, emulate the same thing for a whole range of different incentives. So if, we want to be able to say, you need a new boiler, there's the payback time for your boiler, you should upgrade your building to really have quick changes of energy incentive and refurbishment implementation. So how do we do that when we move from solar radiation to building energy modeling? This is how the UMI tool looks. We start with a massing model, and then we build an energy model of every building in a neighborhood or a city. How do you build an urban building energy model? Well, you need 3 sets of data. You need weather for the city in high resolution, which is widely available. You need to build the geometry, and I should say this is a field where a lot of groups, including groups right under this roof, are working on, being able to do an urban microsimulation, modeling every building in the city. And then the hardest part after the geometry is you have to break up the building stock into different archetypes. So the way we started doing that for Boston, we built an energy model for 80,000 buildings in Boston, where you use GIS data, you extrude the building, you assign a building energy model to every building in the city, and then you run Energy Plus to say how much energy the building uses. And you can get from this kind of funny carpet plots. This is a false color heat map of energy use per area in Boston. And here you see effectively downtown uses a lot more due to its density than the surrounding. This becomes really interesting when you go more to the neighborhood level. So here you see a neighborhood, Back Bay and Prudential Center in Boston, so residential and commercial center. And in gray, you see for the hottest day of the year by time of day, the electricity use for the whole neighborhood, which has the typical graph that you've probably seen in the past. When you have a building stock with a lot of air conditioning, then in the afternoon on the hottest days, you tend to use the most electricity because the air conditioning is on in residential and commercial buildings. And here in yellow, you see if we were to cover a third of all rooftops with PV, what the electricity yield would be. And so the result from this is this so-called Duct Curve that shows you that there's a mismatch between when we use electricity and when we have PV offerings, which is a technical problem for the utility because in a few hours they have to ramp up their electricity production, which is costly and destabilizes the grid. So in this case, we just said, if everybody who gets a PV system has to allow the utility to change their thermostat settings by a few degrees, how much would that reduce the electricity use? So we are starting to use the buildings as a big battery and buffer to avoid electricity use. And you see basically we can reduce the peak with this measure, which effectively doesn't cost anything, We have to overcome some privacy limitations, but apart from that, there's nothing else really that you have to invest in. You see that reduces my peak by as much as covering the third of all rooftops with PV. Now, interesting, in New York City, ComEd just started this. So they have some deal with some of their customers in New York that if they allow some thermostat control, then they get some incentives back from them. So it's not out of the question that you can do things like this. Now, I hope you are critical and wonder how reliable these results actually are. And here's some work that we've done on trying to find that out. So our first study here shows a neighborhood in Kuwait where we worked on, and this is the measured energy use intensity of buildings. So what this shows you, these are all residential buildings, that there's a dramatic spread in energy use from 50 kilowatt hour to 550, even though these buildings seem to be very similar. So that's what we want to model. And in order to model that, we started off just having one building type and one type of occupancy. Then you see here in light gray the measured energy use, and in dark gray the simulated one. So this wasn't very good. Then we started using multiple building types, older buildings, new buildings. That improved our results. But ultimately, we only got really good results when we started introducing something that's called a Bayesian calibration, where we start to model the behavior of people in buildings and develop occupancy likelihoods of how people set their thermostats and so forth. And when you do that, then you get very similar results. We did that. We used our data for this neighborhood to train our model, and then we modeled 2 other neighborhoods, and it worked very well. And we also went into Cambridge, Massachusetts, applied the same type of methodology. And again, for 2,500 residential buildings, we could show that we can model the spread of energy use in neighborhoods very well with this. And I think I'm going to skip this just out of reasons of time. I think it's very important then to say, once we have a model and we spend years on developing calibrated models, what can you actually do with a model like this? So in Kuwait, we went to the Kuwaiti government who had hired us for that, and we showed them, well, could you reduce the energy use in your whole country by 85% with these various upgrades? And they said, that's great. Is it going to pay for itself? And it doesn't when you just look at how the price of electricity is 0.01 cents per kilowatt hour. It cost them 60 cents to create it, so that's not a winning proposition. So after some back and forth and discussion, here's this symposium that we held there. Then only 2 weeks later, they announced that they would raise energy prices. And not long after, there was a big backslash, and nobody wanted the energy prices raised. And does this really matter? What are the payback times? So then we showed just by how much you would have to raise energy prices to make it worthwhile. And at current level, the payback time is 45 years, so longer than the equipment would last. So they have to obviously upgrade it to higher energy prices. That convinced them, and then, unfortunately, sad ending to the story, they raised the price for energy for the expats, but the Kuwaitis still have the subsidized energy. That was not what we recommended, but it tells you that how we can start getting into influencing decisions, hopefully in more productive ways than this, but that you can use this for this. So 2 more projects that I wanted to talk about. I try to be in time for them. We don't only want to look at energy use, but I think access to light is equally important. So our modeling tool can give you availability of daylight for a whole city in a relatively short period of time. So we wanted to basically revisit last year the urban zoning laws in Manhattan. Manhattan was the first city in the world that had zoning laws for access to light and air. And last year they turned 100 years old, where basically 100 years ago they figured out if we keep on building denser and denser, we won't have any fresh air and light on the street level anymore. And if you think of buildings such as the Rockefeller Center, they are basically built to the maximum height that you are allowed to build in Manhattan. So we wanted to see can we build denser in Manhattan without destroying access to light for everybody in the city? Because we want to densify cities, right? We have 2 million new city dwellers every week. If we don't densify, we spread. So we need more people. So can we densify Manhattan? And in order to test that, these are typical Manhattan street blocks. We have different typologies and we let them grow. These are kind of this pencil towers that you see next to Central Park right now popping up. And these are different other high-rise modes. And here, this graph summarizes for you for these different typologies with increasing density, how much access to daylight do you have? And you see that different typologies get very different results. Some fall off our cutoff of half of the buildings are daylit very quickly, whereas others keep on growing. So if you build with these thin towers with a commercial base at the bottom, effectively you can reach daylighting levels up to an FAR of 25, which is twice as high as what you can build in Manhattan right now. So this tells you that when we use this performance-based analysis to urban zoning, we can potentially actually get a lot denser without influencing quality. Of course, interesting, if you convert that into value, that would be per city block in Manhattan, Midtown, $1 billion worth of extra real estate that you can build. So that caught the attention of some of the developers, so we're trying to that now out how well this would work. Last project that I wanted to talk about and show is really going beyond. Again, I'm coming back to Alpha and Jamie. Where are people sitting in buildings? And of course, we've paid a lot of attention to modeling energy use in buildings, and we make assumptions when people are in buildings. But I mean, just from my subjective Erlebniswelt, I see my students at the pub more or at the cafe more than in the lab, because people prefer to work in different environments, and that's fine as long as they work, right? And we wanted to basically understand better what's the flow of people through buildings and cities. And then really our reasoning was we can design this well-daylit spaces. What is it worth if nobody's in the building? So in order to understand movement through cities, we picked the MIT North Court here. And that's a court on the MIT campus that's related between the Stater Center and the Koch Center. It's a really good location for our experiment because in both buildings there are restaurants and cafeterias, and people can sit inside or outside on these benches, which are in the sun and not in the sun. So now we, for a whole year, wanted to understand when are people eating outside and how does this relate to current condition. In order to do that, we used this product called SUFA. This is a spin-off from the MIT Media Lab. This is the CEO of SUFA, Sandra Richter, with our president at the time. And this is a bench. You see a lot of them in Cambridge right now. They are solar powered and you can charge up your cell phone. This also collects a lot of data on the city. So we used 3 of these products here, here, and here, and kept it running for a whole year. And what this does, it has a Wi-Fi scanner in it that captures when people walk by with their phone. So kind of privacy in the modern age. So if you have any smartphone and you don't turn off the Wi-Fi, it basically shouts into the world non-stop, I'm a phone, and this is my Mac ID. And we were allowed for this experiment to collect that. I should say this is not only legal, a lot of companies are doing that non-stop, and they're doing even more. They don't only listen, they say back, when your phone says I'm a phone, they say I'm a router, and then they can see when your phone logs in any network that you've been on, in many cases. So this just shows we need better legislation in the world to protect us from ourselves. But in this case, this is what we collected, just to understand what can we understand here. But we encrypted the information, so there's no way of going back to the actual owner of these devices. And this is what we got out of this. So we collected in this court, in 11 months, 30 million probes, and then we had to clean them up, so we ended up with 14 million unique probes. We threw away the weekends, we only wanted the weekdays. And then it got interesting. First, we could throw out any urban infrastructure that has a MAC ID, but that's not a person. That might be sprinkling system. There's all kinds of, a lot of urban signal in the world. And then we ended up with 670,000 visitors to the space and 16,000 regulars. And regulars are people that keep on coming back, at least once every 2 weeks. So this is really the group for whom we design our cities, right? Because they come back to the same spaces, and when we do changes to urban planning, they actually are more likely to come back again. Whereas the visitors, they come in the snow, in the rain, they just come to see MIT. It doesn't matter if they are comfortable or not. It doesn't change their behavior. Well, that got across wrong. It doesn't change their behavior. Whereas for these, we really wanted to see it right because they have a choice. Do they want to be inside the court or not? And so for the whole month, for the whole year, we measured the outdoor comfort distribution within the court with a metric called the Universal Thermal Climate Index, which is basically an equivalent temperature that tries to summarize everything you feel, the wind, your clothing level, everything, and predict how are you going to feel within the space. And here you see, for example, this changes over the course of the day. In the middle, it gets really warm because there are no trees in the summer. So we can, in a pretty high resolution, in principle, tell if people are comfortable or not. And this graph here took us 1.5 years to create. But this maps for 16,000 people, depending on predicted outside conditions, how likely they are to be outside. So you see really an incredible correlation there, which means that this UTCI metric is really an excellent metric to predict behavior of people. So why we are doing all of this is, of course, that now that we know this metric actually works for that many people, we want urban planning teams to use them to design better outdoor spaces. Because we can, with a very high resolution, predict these numbers. And that way you can effectively say how long are people going to stay outside. How can you make better public spaces? I think this is my favorite graph from that paper, because we also wanted to know, well, how long do people stay for lunch depending on weather condition? And at MIT, the median lunch break from terrible condition raises from 8 minutes to 12 minutes when the conditions are divine. So we have a relatively short improvement. At least some people start having 20-minute lunch breaks when the weather is really good. So right now we're trying to do the same experiments in other cities in the world. Hopefully we see a slightly more sane effect on this. But this, of course, helps you to predict how long are people out there. That makes a lot of, that's very useful from a commercial level. Where should you place your cafes and so forth. And I'm nearly done, Paul. The last part that we started looking at, how do we actually feed our cities, because food obviously has a key impact on the amount of water that we use, amount of land that we are using up. Then food gets transported longer and longer to our destination. And this is probably the worst statistics, how that only 1/3 of the world population has a healthy weight. About 1/3 weighs too much, and 1/3 doesn't weigh enough. So how can we start with cities, making cities better, where we can eat less, or we can eat more local food, and maybe grow food less energy intensive. And that's really the last two is what we wanted to change. So we developed a model that predicts, based on any type of greenhouses, how much food you can grow within cities for urban agriculture. So you can either grow just on urban rooftops, you can use conditioned rooftops, or you can even start having greenhouses in basements and using LEDs to grow food. And it's really striking. With modern LED technologies in certain surroundings, it becomes environmentally better to grow tomatoes with LEDs in basements than what we're currently doing, because the food miles are so enormous. So I think this will help to contribute to rethinking maybe the urban relationship to food and just how we should set up our infrastructure. And this was a fun project where a group of students looked at rooftops and said, should we grow food on rooftops or PV? And actually food tends to win because you create a lot more jobs within the city, whereas the PV you could have outside of the city and just move in with a wire. So this was a quick snapshot of our work. I hope I could convince you that the tools that we currently have are reliable and have been validated so that we understand light and energy within buildings. We have some metrics in place, even though I would say there's definitely a need to become more and more nuanced. What does visual comfort really mean? And that, I think, is a topic where designers should do more work on. And at the environmental performance level, at the urban level, we are now at a point where we can use these tools to make more informed long-term decision-making processes. Where do I think is all of this going in the long run? And this is, I guess, our latest suite of tools. Effectively, I think we already have for some larger buildings live digital building models. Now we want to build a digital model live of whole cities. And then I guess the latest step is that we started with that with Philips to model apps that take the digital model of the city and that feed that back to the individual. So when you are sitting at work, it could, I mean, my watch already tells me when to get up. Then it could basically tell me, go to this bench over here. It's your favorite bench. It's comfortable outside, so that basically this whole digital information that we are collecting guides us through our daily life, hopefully in more productive ways. And let's see where this is taking us. Thank you.
Thank you very much, Christoph, for that very illuminating presentation. I want to take issue with one point, which is that I do think the weather affects visitors in Boston.
Those who survive it.
When I last visited you, it was minus 20 degrees. I can assure you, it did change the way I approach the city. But,
that's true.
So with that, I'd like to invite questions for Christoph, and we'll perhaps take 2 or 3 at a time. Well, let's start with Daniel at the back. Oh, sorry, if you can say who you are. I just said who you were.
Daniel, working here. Thanks for a really interesting talk, and especially seeing an overview of a lot of the small projects that you're doing, well, not small overview of your projects. One thing I was interested in was if you could talk a little bit about, in particular, the occupancy and the kind of behaviour work that you're doing going forward, which is to say that if you think if any research that someone might have done 20 years ago about the way people use offices, the kind of technology they have at home, the way they behave outside. Technology has changed so much that actually assumptions or analysis that or data that might have been collected even 10 or 20 years ago is possibly already quite out of date. I was just wondering how you see that sort of affecting or not affecting your work, and how that sort of thing works if you're moving towards a kind of data that has a long-term use.
I think we're moving towards a more integrated model where we will have agent-based modeling for people within the city that are going to move throughout the city, and then depending on how much parks and walkways we are designing, we can predict how much these are going to be used. And I think tools such as the sofa bench here are really incredible because cities don't have that information right now. They just put these sofa benches into Central Park, and the city of New York has no idea how many people are using Central Park. And that's, of course, this big friction, because I'm sure Google could tell them how many people use Central Park. And we should give the data back to the cities, as if we assume that cities have our best interests in mind in getting towards that. And one example of a project that is not published yet, so I didn't talk about it. We worked with a colleague called Marta Gonzalez, who had cell phone data, I think, for 5 million people in the Boston area for several weeks. So she developed a model of people movement throughout the whole Boston area. And we just worked with her and applied it to a neighborhood that I showed and modeled occupancy. It really showed that we have no idea in our typical models how buildings are used. If you use the standard ASHRAE compliant occupancy models to fill up all the buildings in Boston, you get 5 times more people than there are really in buildings. So we have, I couldn't believe it for the first time. There are 5 times more that we assume, because we assume that people are everywhere, and they are not. than in reality. So I think these type of models will help us to get towards this integrated vision that I just described.
And the microphone, so I'm going to start here and then move over.
Hi, yeah, thanks. It's a really good presentation. I like the example of the benches.
Yeah.
I guess it's a passive method of occupants supplying data.
Yeah.
Have you seen examples of occupants actively supplying data in terms of being encouraged to do so by providing information, and how is it best done in practice?
Yeah, that's a hard question, right? That we knew we wanted to get a lot of people for this experiment. And at first we thought sending emails to the whole MIT community, and we were discouraged very quickly to not do that. But it's hard to get data, I would generally say. What I like about the super bench is that they really are not invasive. And I didn't talk too much here about this, but our whole paper is about how we could have saved a lot less data and still do the same type of analysis. We could have basically only saved always data for 2 weeks and throw it out afterwards. We didn't know that when we did the experiment. But these are just examples of how we could make something like this work everywhere. So right now the city of Cambridge wants to put these benches actually in some areas, because when they have an event that they plan out, you know, Happy Farmers Day Friday or whatever, the people don't have a sense, if the city invests in something like this, how many more people do actually show up. And these benches can give you this information very, very quickly. So I think that's a good example of where to do them. A lot of people actually ask, we tried and failed. We had 3 benches, right? Because we wanted to triangulate where people are. That's actually not possible right now with these benches. And we wanted to know if people are sitting under in the shade or not. We did not get it to work, but I think this is where you see a lot of this research going at next, because a lot of people want to know right now in the research world where people are.
Hello, I'm Miles O'Brien. I'm a MSc Urban Regeneration student.
Mm-hmm.
I'd like to ask, from your experience of working in Kuwait,
Yeah.
they have very good traditional forms of master planning, which allows for calling of the city.
Mm-hmm.
I've seen speaking to other people about this as well. It's
Yeah.
quite, interesting. So why will it ever be used, do you think, in master planning rather than these kind of very expensive technological, kind of, how do you call it, kind of interventions?
Oh, that's my fantasy. I mean, I really want to use these tools. The money is in operational energy use that funds our research. I think it's really interesting to use these tools for urban planning decisions. And in our class, we always try to do both. First, we design a neighborhood in a studio, but then we say for a few weeks, now imagine you are the city. How could you make good zoning laws to encourage good behavior? And I wish these tools would be used more for that. And this is why for New York City, we started with this example, and I think you could do the same for overall massing in the city, how you distribute programs, how many cafes should you have along what corridors. I would love it to be used that way. I think for that to happen, and we talked about that this afternoon, you need a good digital model of cities that is maintained live. And the GIS is a good start, but there are some extra pieces of information that we would all like to have. And right now with the city of Lisbon, we try to convince them to collect this few data points as well. And it's this back and forth. You basically have to convince the city that it's worthwhile doing if you create a lot of extra value. But absolutely, I would love it to be used for zoning. Yeah.
Any more questions?
Maybe just on the education aspect of it, one thing that's very interesting is in first year of architecture, usually there's a very precise brief and everyone gets the same instructions, and there's 100 completely different responses to that.
Yeah.
If we move towards something that's more data-driven, how would you counteract the fact that every student will come back with the same project and same conclusions?
Oh, I love that you asked it. That's one of my pet projects, because that doesn't happen at all. We actually had a thesis once, is is solar architecture a straight jacket for architecture? And that, you know, when you use rules of thumb and you kind of pseudo-wise want to introduce energy efficiency in buildings, then all buildings stoically look south and you have this overbearing mantras at work. When you actually, with modern materials, I mean, we're building modern buildings, design a building, you have an incredible amount of flexibility. It's actually, the students are disappointed how little the massing of the building drives their energy use. That's where we are nowadays. So it's really, and we have to keep, there's always, when we have this whole large group of students playing the game, some have understood it, and I said it a couple of times in class, you know, you have to concentrate on how you put your building together. Dimming controls are more than anything else, put an R value. The worst you can do is use the cheapest building possible and play around with the massing, and then you think you've optimized something. Because the moment when you have a good building standard, you still have all the freedom in the world. I think the tool really helps you to celebrate diversity and show I can do energy efficiency anyway in many different facets. Yeah, really play it. It's more that there's disappointment because students want to see if I look south, I should save a lot of energy, and very often you don't.
That's because the other three faces don't face south.
Yeah, exactly. That's why, right? You can play a little bit with the window to wall ratios and so forth, but there are a lot of limits to it, right?
Any more questions?
That's exactly it.
Okay, well, perhaps we'll get some. Oh, sorry. Yes, there is.
Thank you. My name is Seth Landau. I'm a consultant and potential PhD student here.
Okay.
I work a lot with developing countries, former Soviet space, former Yugoslavia, and whatnot, where there's a lot of dilapidated old infrastructure, old industry areas, and one of the things that we are working with them is how to develop those areas in such a way that will attract both businesses, tourists, people to live, etc., and then also in a sustainable, from a sustainable vantage point related to transport. And I'm wondering how much of your energy model have you tried integrating with the transport model and seeing kind of what are the impacts of the architecture on the foot traffic versus, for example, bus links and or other transport links and that sort of thing.
No, it's a great question, and we've tried that a couple of times because this is, of course, where I really want to be. I want to start shaping the streets and then also see what the impact on transportation is. I guess our most success has been so far with this outdoor comfort model. Now at least we can tell if people are comfortable. We're going to start putting these benches everywhere around campus to be more able to see what routes people take and how many people take public transportation. And that could help on the one end. We have tried also a couple of times, I'm not sure if there are any transportation modelers here. See, even if we model 500 buildings, we are a teeny dot in most transportation models, which is our problem really. The scales are just so different, and I haven't found a good way of linking it fully. I think with comfort we can get towards this, and we can say at least there's an opportunity for biking and taking the bus and so forth, but I haven't found a good way. But I'm very curious in learning more. It was always a scale issue for us.
Thanks very much, very good talk. A few years ago we did a project in which we put Bluetooth dongles to lock people movement in Bath, actually.
Yeah.
And left them out for 18 months. The beauty of Bluetooth is it's very short range. And so you get a very precise relatively precise location for people. Have you thought about doing something like that? Because Wi-Fi can go 100 meters. I imagine you're logging people at quite some distance from your sofa.
Yeah, with the sofa we know, and we tested that out, we know if people are outside or inside. And that's really what, in this case, we were mostly interested in. We were hoping with the strength from the Wi-Fi that we could triangulate. That doesn't work so well, mostly because all the different, if you use Android or smartphone, they all have different signals, so that didn't work very well. I mean, the attraction of the Wi-Fi is that you can track individuals. You give them a number, and if you do it long term, you know if they are coming back. That's what you couldn't necessarily do with Bluetooth. But
you can with Bluetooth, you get
yeah, no, I think that, yeah, no,
that's what we did.
it's a good idea to do it.
Because what you could do then is see if people within 10 meters of each other,
yeah,
were they co-present when they got to the next one,
yeah,
yeah, or were they
yeah.
going different directions?
Oh, that's super interesting.
A
Yeah.
social network
Yeah.
of who was co-present with whom in space over a long period.
And I thought my research was scary.
This was way ago.
No, I think this is super interesting.
Before people started worrying
No,
about that.
I think this is very interesting. Yeah.
Hello, Dan Ringelstein. I'm an architect and urban designer at practice now, MIT alumni. It's great to have you here. I'm very interested in the point that was made about using this as a design tool, not just a measuring tool. It's using it as a measuring tool is very important. Obviously, to understand how people are using spaces to make the next one better.
Yeah.
But I do think it's possible to use as a design tool. The challenge I think we have to overcome is how long it takes to build a model and the context around which you may intervene within. So how long does it take to build a model of a large city environment or a district in a city, and how can that be sort of streamlined to get past deadlines which are now, by the time your model's made, we're done with the project.
I think these are, I get great questions here. Wonderful to be here. No, that's what we really drive. So this, go to our website if you know Rhino. We are using every year in the spring, we have this urban modeling class. We've done dozens of neighborhoods by now, and it goes very fast. I mean, it really is because you can, with a GIS file, you basically can auto-generate a whole neighborhood. And then you have a central part that you are basically working on, right? And then you can just scrape the internet and get amenities for where all the stores are, which we sprinkle then in. If you know how you're doing that, you can do that in 2 days for a whole neighborhood. And then you start designing yourself. What you need is a good building stock description. And this is why, and this is what you have to redo. When we did that in Kuwait, we obviously had to do something else than in Boston and in Lisbon. And there my hope is, and I already talked with Paul about this, if we start having a public library where at least we give our assumption out in a simple format, and then if you want to model London, then you just grab it from UCL, load that in, and then you have all these typologies already there in place. And then it's up to you just to define the upgrades. So to what level do you want to build? And then you just go with it. But that's the intention of the tool, that you can do that in a very limited amount of time.
I was going to ask a very similar question
Okay.
anyways. And my question was going to be, how long do you think it's going to be before these tools are regularly used in practice? And what might be the key things that get them introduced?
I think the hardest thing was to find a good client, because we have, through our Diva tool, very good relationship to a lot of commercial AEC firms. And then once a couple of years ago, we offered a 1-week modeling training. And usually people show up. Hardly anybody signed up. So I called everybody and said, why is nobody signing up? And they said, well, this is interesting. We don't know who's going to pay us for designing a whole neighborhood. And I mean, of course, there are certain areas where this might be the case, but generally that's an impediment right now, that there's no clear agency of who's going to do that. That, I think, is one of the biggest drivers for us right now. This is why we are focusing more on campus development, because you have firms that do master planning and campuses. It's just when you design the whole city, and then especially our real estate model assumes you own the city, and how much money do you make? That's there are not that many people running around that can claim that for themselves. Right?
Those things, generating the value stream.
Yeah. I think we can demonstrate the value, but not who would benefit from that. And I think cities, nobody's from the city here, often lack the sophistication in the technology. Many cities.
I'll take this last question.
Stephen Cannon-Brooks from the Institute of Environmental Design and Engineering. We had a staff meeting this morning talking about what our group objective was. and in the centre of the diagram popped up the words health and well-being. And you very eloquently provided a case for energy-based analysis. If we start to move beyond that to criteria which we're still grappling with what they mean and their implications, where do you think your modelling may take you? For instance, you have no acoustic modelling.
Yeah. Very true.
Comfort is not just the only thing.
No, it's very true. I mean, where's it going to take us? We've been working a number of times with the Harvard School of Public Health, and they recently came to us that they can help us model the extremes. So in terms of thermal comfort, think back of 2003 when it was too hot in Paris, the mortality rate goes up. So we're actually pretty good by now at saying what is too much. Which is kind of, we also think in comfort in terms of the worst discomfort. That seems to be in the scientist's mind first. So I think this is how we're going to start, that we just describe how with climate change, where are we going to have the weak spots within cities where discomfort is going to be a key issue, and apply that. And for example, Lisbon is there a good case study right now. In Lisbon right now, energy use is very low, but it's very likely that in the next 20, 25 years, due to climate change, it's going to be just warm enough that everybody has to buy an air conditioning system. And then there's the issue of energy poverty there, and how do you deal with that? I think these are our ways in at the beginning. The reason why we don't do acoustics is we have been talking to various acousticians and acoustical modeling firms. It's not that an established field. The tools that we found are mostly big commercial tools, and it was hard for us to just link them in. I would love to put them in. I think these models would be great to see how loud is the city, and then you could show if everybody had an electric car, how much quieter the city would get. These arguments we could build then.
Right, I'm going to call a halt to questions there. Please join us for some drinks and nibbles afterwards, and to say thank you again to Christoph for an excellent lecture.
Thank you.